Question number 8. Describe and explain what would happen to a cell containing 100 millimolar of NaCl, 150 millimolar of glucose, and 100 millimolar protein if the cell is placed into the following different solutions with different cell membrane permeabilities. So this is the most essential and difficult type of question that we're going to have in this workshop. Whenever we are given this type of questions, we want to think about two separate processes. The first one is diffusion. The second one is osmosis. So the simpler ones in among the four following scenarios are A, B, and D, because the permeability in these scenarios of cell membranes is only to water. So you don't have to think about the process of diffusion of different solutes. You can only focus on the process of osmosis, which is the net movement of water. If you still remember, the direction of osmosis is from hypoosmotic solution to hyperosmotic solution. Or you can say it's from a lower osmolarity to higher osmolarity. In any case, osmolarity should be the only parameter that you use to tell the water movement, at least at the beginning stage. Okay, so we're going to look at scenario A, B, D at first. Before we actually go into any specific scenarios, we wanna know both the inside and outside solutions osmolarities. The cell is a solution of three mixtures. A mixture of NaCl, glucose, and proteins. You have the molarity of the three solutes inside. The only thing for us to do is to calculate for the osmolarity separately for the three solutes and then add them up together. We can assume complete dissociation for the convenience of calculations. So for NaCl, if we assume complete dissociation, the dissociation constant would be 2. The molarity of NaCl is 100 millimolar. We multiply the number by 2, the dissociation constant, to get 200 milliosmolar of the osmolarity of NaCl. For glucose, the dissociation constant would be 1. So the osmolarity for glucose would be 150 milliosmolar. Protein is similar to glucose, which will have a dissociation constant of 1. So the osmolarity of protein would be 100 milliosmolar as well. When we add up these numbers together, these osmolarity values together, let's see if we have it here. Okay, so we have 200 milliosmolar for NaCl, 150 millimolar for glucose, and 100 millimolar for protein. In a total, we have 450 milliosmolar as the overall osmolarity of the cell. After this, we can compare this number with the outside solution. Whichever has a higher number is called a hyperosmotic solution, and you can make the judgment of osmosis. Since osmosis is always going to be flowing from a lower osmolarity part to higher osmolarity part, the solution to question A, B, and D would be very simple. Okay, scenario A. If the cell is placed into distilled water and the cell membrane is only permeable to water, the outside has an osmolarity of 0. In the contrary, the inside is 450. So we say the outside is hypoosmotic to the inside of the cell. So water will move from outside to the inside of the cell. So the cell will swell and then eventually burst. Second scenario, if the cell is placed into 100 millimolar of NaCl and the cell membrane is permeable to water only. First step, we should calculate the osmolarity of the outside solution so that we can make a comparison between the outside and the inside osmolarity. When we have 100 millimolar of NaCl, we can simply multiply the number by the dissociation constant of NaCl, which is 2. So the outside NaCl solution in this scenario is 200 milliosmolar. In a comparison to 450 milliosmolar to the inside of the cell, the outside of the cell is still hypoosmotic to the inside. So water will flow into the cell. The cell will swell and may eventually burst, depending on how strong the cell membrane is. Okay, that's the answer. We'll look at scenario D first. I'll leave the most challenging scenario C at the end. Scenario D, if the cell is placed into 200 millimolar of glucose and the cell is only permeable to water. Okay, the same steps to scenario B. We should calculate for the osmolarity of the outside solution first, which is 200 millimolar, times 1, which is the dissociation constant of glucose. That'll give us a final number of 200 milliosmolar. 200 milliosmolar as the final osmolarity of the outside solution. Compared to 450 milliosmolar in the inside of the cell, the outside is still hypoosmotic to the inside of the cell. So water will move in. The answer will be the same as question 8b. Okay, let's move back to scenario C. Scenario C has an outside solution of 100 millimolar of NaCl. We should still calculate for the osmolarity of the outside solution, which is 100 millimolar times 2. That gives us 200 milliosmolar as the outside osmolarity of the NaCl solutions, of the NaCl solution. The only different part of this question is the permeability of the cell membrane. So it is said that the cell membrane is permeable to salt and glucose as well as water. So the only thing that's listed in this question and is not permeable to the cell membrane is protein, right? The cell contains NaCl, glucose, and proteins, and water, of course. So the cell membrane is permeable to all the other solutes except for proteins. Okay, step 1 is the same. We should still calculate for the osmolarity of the solution, which is 200 milliosmolar. But step 3, we need to think about 2 separate processes: osmosis and diffusion. Okay, so osmosis, at least at first, we say that the outside solution with a 200 milliosmolar of osmolarity is smaller than 450, which is inside of a cell. The outside solution is hypoosmotic, so the water will flow in. That's the direction of osmosis, at least at the beginning. Water will flow in. And then let's look at diffusion process. Since we have all these three components, three solutes in the environment, in a scenario, we want to look at the diffusion of them one by one. First of all, the diffusion of NaCl. If you still remember, the process of diffusion is irrelevant to the process of osmosis. It's irrelevant to the overall osmolarity of the solution. It's only related to the concentration of the specific particles that we're looking at. So in solution, we're going to have Na ions, Cl ions, glucose molecules, and protein molecules. The diffusion of Na ions is going to be determined only by the Na ions inside and outside the cell. So both inside and outside has the same concentration of Na ions and Cl ions, at least at the beginning of the process. So there will be no diffusion of Na and Cl ions at the beginning of the process. How about for glucose? We have some glucose inside of the cell, but we don't have any glucose outside of the cell, right? So glucose will flow from inside of the cell into the outside of the cell. If the outside of the cell has much greater majority of solution compared to the inside, then the final concentration of glucose, both inside and outside, will be very close to the outside, to the original outside concentration of glucose. In this case, will be 0. This is a little bit tricky part. If you can't understand it, we can discuss it after class. But please remember that if the outside solution is a vast majority compared to the inside, then the final concentration of the diffusion process will be the same as the original concentration of the outside solution. In this case, when glucose flows out of the cell, the final unit, the final concentration of glucose will be very close to 0, both inside and outside of the cell. Okay, so for proteins is not permeable to water, so there will be no diffusion of proteins in this scenario. Okay, so we know that at the beginning there is some diffusion happening and there is some osmosis happening from the outside to the inside of the cell, right? So since the water will move from the outside to the inside of the cell, that will dilute the NaCl concentration. That will lower the NaCl concentration inside of the cell. So as the time goes by during the process, the NaCl will have lower concentration in the inside of the cell. It'll be lower than 100 millimolar. But the outside will always have 100 millimolar of NaCl. So there will be some diffusion of NaCl into the cell along the process, trying to make equilibrium for NaCl, trying to reach a same concentration inside and outside for NaCl. The inflow NaCl will increase the inside osmolarity of the cell. So some water in the outside will follow the movement of NaCl, try to balance the increasing osmolarity of the inside of a cell. So when the water comes into the cell, the NaCl solutions, the NaCl concentrations will be lower again. And the NaCl in the outside of the cell will try to follow the water to compensate for the imbalance NaCl concentration in the inside and outside, and then the water will follow. So that's like a loop. Once the NaCl comes into the cell, try to make equilibrium the same concentration of NaCl for itself in the process of diffusion. This process will increase the osmolarity inside of the cell. So more water will try to follow the process. The water will try to reach equilibrium in the process of osmosis to compensate for the increasing osmolarity inside of the cell. So NaCl goes in, water goes in, NaCl goes in, the more water will goes in. By following this rule, these loops, the cell may eventually burst. This is a whole process, and this is the most challenging question of workshop question 8. It is very similar to some of the questions in question number 9. We're going to have a chance to review it in question 9, and you'll have more of an understanding of this type of question.